So the motivation for rainfall runoff modeling, as I said, is generation of synthetic river flow data, depending on assigned input data, which in general are rainfall. But rainfall is always present, but very often there are other types of input data, like temperature. We will see more in detail soon what kind of input data we may have. And as I said, the motivation is that in general, rainfall data are more easily available than river flow data. And the reason for this is that to measure rainfall is much simpler than measuring river flows. Basically, as I said, we have different type of inputs, and inputs may include catchment behaviors, like catchment extension, like land use, vegetation cover, soil type. These are the main behaviors of catchments that are used in rainfall runoff modeling. And I consider this kind of data as input data. This is a general view, because some people, when they say input data to rainfall runoff modeling, they just mean meteorological data. In a general and broader view, you can include also catchment behaviors. And also you may have river network behaviors. Like the geometry, the shape of the river network, which is needed to model flow routing, meaning the propagation of flows along the rivers. We already defined catchment, correct? Catchment, I said, that is given by the topographical surface such that the rainfall and only the rainfall falling on that topographical surface contributes to the river flow in a given cross section. Then we have river network behaviors, and then we have meteorological data. Including, as I said, rainfall, temperature, and so on. Rainfall is always present, because otherwise it wouldn't be a rainfall runoff modeling, of course. Temperature is almost always present, and other type of meteorological data could be present, like snowfall, which is sometimes included in rainfall. When one says rainfall, in general, one implies precipitation. Precipitation is, in general, rainfall and snowfall. But meteorological data could include also wind data to compute evapotranspiration and so forth. Depending on model complexity, of course, you have different types of input data. The minimum requirement, the minimum data requirement usually is rainfall and some basic catchment behaviors. Even if you can reduce really catchment behavior to almost no data. Because as you will see, there are very simple rainfall runoff models that can be set up by just using rainfall data. But the vast majority of the model includes some catchment and river network behaviors. Now, what is our target? Our target is to set up a mathematical relationship which is the model, such that you give data to the model and you get river flow. This is what we need. And this box that I called model can be of different types, of course, and in general is given by a system of equations. Minimum of one equation, in general, a system of equations. So it's a mathematical model. The need for rainfall runoff modeling was emerged in the far past. Already almost 200 years ago, population felt the necessity, the need, to compute in very simple ways, of course, the rainfall runoff transformation. Because at that time, more than today, they suffered the lack of river flow measurements. So they had the first necessities to design structural works like bridges, like flood protection measures, and they needed to get an estimate of the river flow, but they didn't have any measurement, while they had some measurement of rainfall. And the first need that humans had was the estimation of peak flows, maximum flows. Because at that time they didn't have many needs about water resources management, but they had the main need to protect themselves against floods. So they needed an estimate of peak flows. So the first rainfall runoff models that were conceived by humans were finalized, were targeted to the estimation of peak flows. And the first type of relationship that they set up was empirical. The first idea that one has to set up a mathematical relationship of this type is to devise an empirical relationship. Just look at the phenomena, the natural phenomena, and try to understand an empirical relationship, try to set up an empirical relationship, try to understand what happens, and consequently to set up an empirical relationship relating the rainfall to runoff. And I would like to mention the first one, empirical relationship that was proposed, which is indeed the first rainfall runoff model, because I think it's important that I start from the empirical point of view to clarify what is the nature of this relationship. And the first one, which was proposed, this is a debate, an historical debate, because some people say that was proposed by an Irish hydrologist in 1859, and Americans say that it was proposed by an American hydrologist, of course, 20 years later, around 1880. Probably they independently derived this empirical relationship. And what is this empirical relationship that dates back to about 150 years ago? It's the rational formula that for sure you already know, because you have some basic, more than basic, some knowledge of hydrology. The rational formula says that the peak flow at a given, let me call it QP, and I'm not highlighting the dependence on time in this case. The river flow depends on time in general, but in this case that we obtain an estimate of the maximum flow that is expected in a given cross river section. And therefore in this case I'm not highlighting the dependence on time. When I refer to a peak flow, the dependency is only on the geographical location, not on time, because I'm not interested in the timing of the peak flow. I'm just interested in the magnitude. So the QP is given according to the rational formula, which is called the Newtonian formula razionale. Is given by the product of a coefficient C, we will see the meaning, times rainfall intensity I, times the area of the catchment A. It's also called CIA formula. And the rational formula highlights an intuitive result, namely that the peak flow depends on the catchment extension, on the catchment area. And also, of course, that peak flow depends on rainfall. Now, let's suppose that you have rainfall intensity, okay? So it's the unit measure of I, rainfall intensity, is a distance over a time, typically is millimeters per hour or millimeters per day. It's an intensity of rainfall. And let's imagine that you have a uniform rainfall over the basin, over the watershed, over the catchment, that lasts for a long time period, let's say an infinite time period. It is intuitive in this situation that if you multiply this rainfall intensity for the area of the catchment, then you obtain a volume of rainfall that falls over the catchment per unit time. Because in this case you have a rainfall intensity which is, again, a distance. If you multiply by an area, which is distance, square distance, then you get a volume. And therefore you get the volume of water that is raining over the catchment per unit time. In this case, hours or days. And if you assume that this rainfall lasts for a long, long time, then it's quite understandable that you get at the closure section of the watershed in the river, you get the same amount of water per unit time that is leaving the catchment. You can imagine that you have a balance between the rainfall that rains for a long time over the catchment and the volume of water that leaves the catchment per unit time. A basic pre-requirement, a basic assumption is that rainfall lasts for a long time, because if you have a short rainfall, of course, you have not this correspondence. You don't have time to reach the balance between water entering and exiting. So please note what I'm doing. I'm doing a water balance. I'm computing a water balance. Okay? So I take an assumption, a simplifying assumption, very long rainfall, in order to be able to say that thanks to the concept of water balance, water entering in the catchment is equal to water exiting from the catchment. So this was the reasoning that they did at that time. They said, okay, I'm interested in the computation of the peak flow. Therefore, peak flows occur when you have long rainfall, so the assumption is reasonable. Let me assume that I have a long rainfall. So let me look at measurement of long rainfall, and let me apply this empirical formula that basically is one equation which makes use of the water balance concept. So the idea was, let's compute the water balance. And in this case, you get an equation that forms the rainfall runoff model. So let's think at the idea. They looked for a balance of water in this case. Mass balance, water balance, mass balance, it's also called continuity equation. And then they introduced a coefficient C, because they understood that not all the water that is raining is finally flowing out of the catchment through the river, because there is some water that is lost. They understood that some water evaporates, for instance, even if evaporation is not very significant during rainy days, rainy hours, but they understood that some water is lost. Evaporation could be influential, or another reason for water losses could be deep infiltration. When you have deep infiltration, you may have some water that is lost, and maybe you don't get it back to the river. Maybe that water is stored for millions of years in the earth, and maybe that you get it back in the form of volcanic eruptions or something that is not related to the river flow in the given closure of the catchment. The closure of the catchment or catchment outlet is a synonym for the river cross-section with reference to which you estimated the catchment extension. So when you refer to a catchment, you always refer to a river cross-section, which is the outlet or the closure. In Italian we say sezione di chiusura. Okay? So they introduced this coefficient. And this coefficient is called the runoff coefficient. In Italian it's called coefficiente di afflusso. Runoff coefficient. So C is the runoff coefficient. Now we have a problem here, because the relationship basically is very simple, you see. But there are some problems, of course. First of all, estimation of the catchment area is not a big problem. If you have a good topographical map and you assume that the topographic divide can be taken as catchment divide, estimation of the catchment area is not a big problem. But we have now the runoff coefficient. We have to estimate it. What is the value of the runoff coefficient? Intuition says that it must vary between 0 and 1. If you think at the definition of the runoff coefficient, it allows you to take water losses into account. It means that it must be lower than 1, because if you get a runoff coefficient that is greater than 1, you get an increase of the water volume with respect to rainfall, which is not reasonable. So it must be lower than 1, and the lower value should be 0, because of course it cannot be lower than 0. But we observe in some catchment values of the runoff coefficient greater than 1. What does this mean? It means that either catchment area is badly computed, is imprecise, for instance, because the catchment divide is not coincident with the topographic divide, or the runoff coefficient can be greater than 1 if you have changes in the water storage in the basin. What I mean? I mean that in our catchment you always have a water storage. Water that is stored in the catchment. So it may happen that during the rainfall event, besides of having water coming from rainfall that contributes to the river flow, you may have also some water that is released by the catchment storage. This means that you have an additional water the catchment is giving to the river, which is not rainfall. It's a change in catchment storage. And therefore you may have a runoff coefficient that is greater than 1, because besides the rainfall you have a water that is released by the catchment. And this implies that if you had the possibility to measure the water that is stored in the catchment before and after the event, you would find after the event, after the rainfall event, that the water stored in the catchment is lower with respect to the beginning of the event. This happens especially if the rainfall event is short. You may have changes in water storage. Typically you have an increase, because during a rainfall you expect that the storage in the catchment increases. But you may have decreased for some reasons, and this happens especially if the duration of the rainfall event is short. Because if you look at the catchment storage in the long period, you don't expect big changes. If you look at the catchment storage, average catchment storage over a year, you don't expect big changes. You expect big changes if you look at one day and a day later, and you look at the catchment storage in that day, which means average storage over a day, not instantaneous storage, average storage over a day, and you look one day later, you may expect a difference. But if you look at average catchment storage over 1 year, and you move forward of 1 year, 2 years, you don't expect big changes. Also, a reason for runoff coefficient greater than 1 could be snow melt. Water that comes from snow that is turning into water. This is called snow melt. Anyway, we have this problem to estimate the runoff coefficient, and the literature gives some indication. For most of the rivers, Apennine rivers, you find values of the annual runoff coefficient, means average value over 1 year, which is about 0.6, 0.5, 0.7. This value is representative of a quite impervious watershed. So don't expect that you have in some watershed values of the runoff coefficient that are close to 1, because you get 1 only if the watershed is completely impervious. And while in many cases, if you get a catchment that is located in a flat area, you get runoff coefficients that are close to 0, 0.1, 0.2. Then, this is a problem. The big problem of the rational formula is the estimation of the runoff coefficient. Of course, you can say, okay, I want to stay on the safe side and I take 1. But in doing so, you get a design variable for your structural work that is very heavy. So it's not convenient from an economical point of view. And then the second problem is to estimate this rainfall, because let's look at the data. You have different rainfall events. So you have to choose which one to feed into this relationship. Of course, each rainfall event has its own rainfall intensity. So if you look at the data, for each event you get different values of I. So now the question is, what value should I put in here? And the reply, of course, is you have to find the value that maximizes your peak flow. If you want to find the maximum peak flow, you have to plug in here the value of I that gives the maximum. So if you have a long series of rainfall events, you should try with any of them and pick up the one that gives the most critical situation. And of course, this is a bit of a problem because, if you have a long series of rainfall data, then to try each rainfall event is time consuming. And what is one of the main behavior of rainfall that you well know? If you look at individual rainfall events, you look at the behavior of these events, you understand that rainfall events are characterized by two main features. First of all, the duration of the event and rainfall intensity. Normally, it is average over the event duration. I say normally because if you want a more complex representation, you may also represent the variation of rainfall during the event. But usually, here you want a constant value, so for each event you get the average intensity. But you will notice, if you look at the rainfall series, that events also differ, not just by intensity, but also for the duration. And typically, if you look at summer here in our climate, you will notice that rainfall intensity in summer is higher, but rainfall duration is shorter. While if you look at autumn, winter, spring, you will see that usually you have lower rainfall intensity for longer durations. And people observed that given these two features, people observed that the rainfall event that causes the most critical condition, usually these events, these critical rainfall events, have a common behavior which helps in identifying critical events. And the common behavior in terms of duration is that the duration of the rainfall event is close to the time of concentration of the catchment. I say again and then I explain. People notice that the duration of critical rainfall events, critical meaning that they induce the higher river flows, the duration of critical rainfall events is close to the time of concentration of the catchment. What is the time of concentration of a catchment? In Italian it's called tempo di corrivazione. It is a basic concept in hydrology, like the concept of catchment, so you have to remember this definition. So the definition is, again, time of concentration. What is the time of concentration? It is the time taken by a drop to reach the catchment outlet by following the longest way. Again, it's the time taken by a drop to reach the catchment outlet by following the longest way. You could also define it by saying it's the maximum time taken by a drop to reach the catchment outlet. A drop of rain. I forgot to say a drop of rain. I think it's implicit, but let's be precise. What does this mean? It means that, let's imagine that you have rainfall falling on a catchment, and if you have a drop falling, for instance, here, you can imagine that it takes some time for the drop to get to the catchment outlet here. And you understand that this time is different if you change the position of the drop in the catchment. And you could think that we assume that the time taken by the drop to get to the closure of the catchment is just dependent on the position of the drop, the catchment, and therefore we can identify the longest time. Typically, the longest time will be taken by a drop that falls on the divide in the point located most far from the outlet. But it also depends on the velocity. So let's say that typically it will be on the divide. And basically, you can understand that if you assume that rains over the catchment and stops raining after the time of concentration, all the water that rained over the catchment passes through the outlet. This is the time of concentration. And therefore, people observe that for rainfall events lasting close to the time of concentration, they got the most critical conditions. Because of course, you can imagine that if it rains over a catchment, if you have a very short rainfall, then what happens? It happens that, of course, you have a very, normally when you refer to extreme events and you have a short duration, then you get a high intensity, because you refer to summer events, for instance. So if you look for the events that are characterized by the higher intensity, they occur in summer, but typically they have a short duration. And therefore, if you think about a basin that has a concentration time of 10 hours and it rains for 5 minutes, you understand that this is not a very dangerous rainfall. Even if the intensity is very violent, this is not very dangerous. Why? Because if it rains, even if it rains over the whole catchment for 5 minutes, then of course you have some drops that are located here that get to the outlet very quickly. But you have some drops that are located very far from the outlet that get to the outlet after 10 hours. But after 10 hours, you don't have any more at the outlet the drops that rain like in this area here. They already passed because the rainfall lasted for just 5 minutes. So it means that all the drops that are located close to the outlet after 5 minutes plus a little bit more, but not much, they are already passed. So you don't have the superimposition of drops that rain here with drop raining here in the outlet. You don't have the superimposition because they can't superimpose, because the duration of rainfall is such that when drop that fell here get to the outlet, we don't find at the outlet anymore the drops that fell close to the outlet. I hope you understand the concept. So this is the reason why a short rainfall is not concerning, even if the intensity is very violent. But if you have a longer rainfall, the intensity decreases, but you start having some superimposition. And think about the time of concentration. If it rains for the time of concentration, it means that you have full contribution of the catchment area to the river flow. Because let's think about, if you have a time of concentration of 10 hours and it rains for 10 hours, then after 10 hours you have all the drops contributing to the river flow. It's clear? So you can understand the reasoning. Still you may be in doubt, because you could think that given that intensity decreases, you could think that maybe that you have critical condition in terms of peak flow for shorter rainfall duration, because the intensity is higher. So you may say, okay, I don't have a part of the catchment contributing, I don't have the whole catchment contributing, I have a fraction of the catchment contributing, but given that the intensity of rainfall is higher, I may end up with a condition that is more critical with respect to that I get when rainfall is lasting as the time of concentration. You may be in doubt. Okay? Let me prove later on that indeed the time of concentration under certain assumptions is the more concerned rainfall duration. Okay, so the purpose of this introduction with the rational formula is to clarify to you what was the reasoning of these people who had first the necessity to estimate the peak flow. And this kind of reasoning is indeed the logical structure that we should always follow in hydrology. Think about the processes, understand empirically the main behavior of processes, and then build the model with the appropriate level of complexity, with the awareness that the model will always be imprecise, uncertain. Now, the rational formula then, it's very useful but doesn't solve our problems completely. First of all, because we have to estimate the runoff coefficient, we have to estimate the critical rainfall event, and therefore, still we have some problems. But, above all, let's note that the rational formula gives us the indication of the peak flow, not of the whole hydrograph. What is the hydrograph? The hydrograph is the diagram of the river flow against time. So typically, the hydrograph shows Q as a function of T, and usually Q, the river flow, is displaced along the vertical axis, the ordinates, and time T is displaced along the abscissa. And you get a picture that is extremely varying depending on the catchment behavior. It's something like that, and which could also be intermittent if you have periods in which you don't have any flow in the river. So, what's the difference when we know the hydrograph with respect to the sole knowledge of the peak flow? The difference is obvious. The peak flow is just a point of the hydrograph. It's the maximum. But for water resources management, we need not just the peak flow. We don't need the peak flows. We need to know how much